Let's get right into it. Welcome to this explainer where we're going to meticulously deconstruct Lecture 23 on soil colloids, translating some pretty dense academic structures into a clear visual blueprint. Today, we're exploring secondary silicate clay minerals, mostly newly formed crystals built from the soluble products of primary minerals, and comparing them all the way up to organic humus. It is a really fascinating journey into the microscopic architecture that's literally right beneath our feet.
Here's our agenda, and it maps perfectly to our source lecture progression. We're moving step by step, starting from the microscopic inorganic building blocks of clay, classifying the different types of layer silicates, comparing some key minerals, examining amorphous and sesquioxide clays, and then wrapping up by looking at the ultimate contrast between organic and inorganic colloids.
Section 1. The Microscopic Foundation. Let's dive right into this and establish the fundamental geometric shapes that build all secondary silicate minerals.
To understand clay, we really have to zoom way in. The foundation here begins with two distinct units. First, we have the silica tetrahedron. Picture a four-sided configuration with one silicon atom completely surrounded by four oxygen atoms. When a series of these are tied together horizontally by sharing oxygen anions, they form what's called a tetrahedral sheet. Simple enough, right? Second, we have the aluminum octahedron. This is an eight-sided building block where an aluminum, or sometimes a magnesium or iron ion, is surrounded by six oxygen atoms or hydroxyl groups. Link a bunch of these together horizontally, and you get your octahedral sheet.
You can see this brilliantly illustrated right here. Notice that single silicon atom sitting perfectly in the center of the four surrounding oxygens on the left? That is your tetrahedron. Over on the right, you see the aluminum ion surrounded by 6 points, oxygens or hydroxyls, making up the octahedron. Now, our source points out a super interesting detail. In an aluminum-dominated sheet, two aluminum ions satisfy the negative charge, making it a dioctahedral sheet. But if magnesium dominates, it actually takes three magnesium ions, making it a trioctahedral sheet. These specific combinations largely control the physical and chemical properties of every clay mineral we're going to look at today.
Section 2. Classifying the crystals. Now that we know the basic sheets, how do they actually stack up to form crystals?
Well, based on the sequence of these sheets, silicate clays fall pretty cleanly into a few main categories. You've got the 1-to-1 type, like kaolinite and halloysite, then the 2-to-1 type, which includes montmorillonite, illite, and vermiculite, and finally the 2-2 type, represented by chlorite. The layers in these structures are all bound together by shared oxygen atoms, and it's this exact arrangement that dictates absolutely everything about how the clay is going to behave in the real world.
Section 3. Comparing key clay minerals. Let's see how these structural blueprints actually manifest, because this is where the geometric theory translates into real-world soil behavior.
Take a look at this stark contrast. On the left, you've got the fixed 1-to-1 structure of kaolinite. On the right, the expanding 2-to-1 structure of montmorillonite. Look closely at kaolinite. It's one silica tetrahedral sheet combined with one aluminum octahedral sheet. The absolute key here is the hydrogen bonding holding the crystal units together. It holds them incredibly tightly, resulting in a fixed structure with zero scope for cations or water to enter between the layers. Now, look over at montmorillonite. It's a 2-to-1 type, meaning an octahedral sheet is sandwiched right between two tetrahedral sheets. Notice the gap? These units are linked by weak oxygen bonding. This means it readily opens up space for water and exchangeable cations to occupy. Plus, our text notes that isomorphous substitution happens here. Silicon is swapped out by aluminum, aluminum by magnesium, giving the whole thing a net negative charge.
The differences in these microscopic structures result in some drastically different physical properties that directly impact nutrient availability and how soil handles water. Montmorillonite's expanding nature gives it a massive internal surface area. We're talking 550 to 650 square meters per gram. Kaolinite, it literally has zero internal surface area. Because of that expanding nature and the isomorphous substitution, montmorillonite boasts a cation exchange capacity, or CEC, of 80 to 120. That completely dwarfs kaolinite, which sits at a measly 2 to 5 CEC. Montmorillonite is highly cohesive, it's plastic, it swells, it shrinks, while kaolinite is low across all of those metrics. And then we have illite sitting comfortably right in the middle, with a CEC of 15 to 40 and medium swelling.
So why exactly does illite sit in the middle? Well, here you go. Just like montmorillonite, it has that 2-to-1 sandwich structure. But check out the inner layer space. You see those potassium ions labeled as K? In the tetrahedral sheet, 20% of the silicon is substituted by aluminum. That potassium satisfies the resulting negative charge and securely locks the lattice structure shut, so it just cannot expand.
We also have to mention a unique outlier, chlorite. This one is a 2,2 or 2,1,1 non-expansive clay mineral. It's basically an iron-magnesium silicate. What makes it so special is that it alternates the standard 2,1 layers with an extra magnesium-dominated trioctahedral sheet. This extra sheet gives it a size and a negative charge that's actually quite similar to illite.
Section 4. Amorphous and schistooxide clays. Moving beyond those beautifully ordered crystals, let's contrast them with short-range minerals. These completely lack a strict, ordered three-dimensional structure.
Let's compare two key types of amorphous minerals. On one side, we have Allophan. These are amorphous aluminosilicate gels, mostly found in soils developed from volcanic ash, where there simply hasn't been the time or condition for good crystal formation. Their charge is completely variable, governed entirely by soil pH, and they can have a really high CEC of 150 in neutral to mildly alkaline conditions. On the flip side, we have sesquioxide clays. The name literally means 1 and 1.5 times. These dominate highly weathered soils in the humid, hot tropics. Examples include gibbsite and goethite. They form these amorphous coatings that give soil distinct red or pink colors. What's wild is that the crystallization of these amorphous iron compounds actually causes the irreversible stone-like hardening of plinthite or laterite upon drying. They are non-sticky, non-plastic, and their variable charges pose a really big problem for phosphorus availability.
And finally, Section 5. Organic versus inorganic colloids. Let's step away from minerals entirely to look at organic colloids, which in soil are primarily composed of humus. 900. A staggering 900 square meters per gram. Let that number sink in for a second. That is the potential specific surface area of well-developed humus. It dramatically emphasizes the sheer holding capacity of organic colloids. Just to put that into perspective based on our earlier data, the highly expanding montmorillonite capped out around 770 total surface area, while kaolinite barely reached 30. Humus is highly colloidal, it's totally amorphous, and it's essentially just made of carbon, hydrogen, and oxygen. Drawing a direct line between the organic and the inorganic reveals this beautiful contrast. Organic colloids come from the decomposition of organic matter, while inorganic colloids come from the weathering of rocks and minerals. The composition is entirely different. Carbon, hydrogen, and oxygen on one side versus silicon, aluminum, iron, and magnesium on the other. Organic colloids are completely unstable in nature, compared to the stable inorganic crystals. But just look at that cation exchange capacity. Organic colloids range from 150 all the way to 400. That is significantly higher than almost all the inorganic clays we discussed. And it's driven by the strongly pH-dependent dissociation of hydrogen from functional groups like carboxylic and phenolic groups.
To wrap up this explainer, I want to leave you with a thought derived entirely from the data we just explored. Considering these vast structural differences, from the locked, rigid hydrogen bonds of kaolinite to the expansive oxygen bonds of montmorillonite, all the way up to the massive 900 square meter surface area of amorphous organic humus, how does this delicate balance of microscopic structures ultimately dictate the physical and chemical reality of the soils we rely on every single day? It all starts right here, with these tiny geometric building blocks. Thank you for joining me on this deep dive into Lecture 23. Keep exploring and stay curious.